Okay guys, so in this video we're going to talk about average value of a function. Now, the average value of a function is very similar conceptually, and to be honest, it's based on it, on the intermediate value theorem from calculus, which basically is a theorem that tells us, if you recall, that if we have some like smooth continuous function, for example, the temperature outside, if we know that the low is, say, 50 degrees and the high is 80 degrees, then at some point in time during the day, we will reach all the values in between 50 and 80. So there will be a time, at least once, during the day where it will be 60 degrees and 70 degrees and 71 degrees and so on and so forth. Like that's a known fact from the intermediate value theorem and from reality itself. So that's always nice when they agree. Now, the average value of a function essentially is exactly what it says. It's this average value. So, while it's simple to compute the average value of a set of finite numbers, we obviously know how to do that. The average we describe as like adding up all the values and dividing by how many there are. We can't just do that when we have infinitely many points, because how do you divide by infinity, right? So, there must be some way, though, of computing the average temperature during a day or the average velocity of a car if infinitely many readings are possible. And for that, obviously, we're going to use integration. So we have a formula. The f average, the average of the function, is 1 over b minus a of the integral from a to b of f of x dx. Essentially, what this formula is saying is that the average height of some function here is equal to the area divided by the width, which, to be honest, makes some sense, because again, this is the area and we're dividing by the width. And so we're functionally finding some like average height of the function. And we use that when we are trying to find this average value. And so this is what I mean by that, is that essentially we take the function here, the area of the function, and divide it by its width to basically create a rectangle that has the same area as the function, but it's been reshaped to be just this rectangle thing. Okay. And so we have this mean value theorem for integrals, so much like our mean value theorem of calculus. We have this theorem that says that if f is continuous on some a to b, then there exists a number c on a to b such that f of c is the average value of our function. So again, the reason this is so similar to the mean value theorem of calculus is that they're based on that concept. All right, so let's actually take a look at how that works. So find the average value of the function 3 cosine x from negative pi halves to pi halves. Now, let's take a look at the graph of this. So we have Desmos 3 cosine x, okay, and we want to take this, so I'm going to go ahead and say f of x is equal to squiggly brackets pi halves is less than or equal x, which is less than or equal to pi halves. I need to do the other one that's negative pi halves. Okay, there we go. So we have this function here. Now, I think that starting with this nice simple graph here, I mean, it's symmetric. So basically what we're trying to do is we want to find like some rectangular object that is the same width that has the same area as this curve. That's basically what is happening here. So we're going to take the area of this function. So if you recall, we have this formula right here. So I'm going to go ahead and snip it and bring it onto the other page that we're working on. Okay, so we are going to take this formula here, and again, what this is simply the area divided by the width. That's all we're doing. We're taking the area of our function dividing by the width. I can't stress that enough because it's that simple. So we're going to take the integral from negative pi halves to pi halves of 3 cosine x, And we're going to take that value and divide it by the width. So from pi halves to negative pi halves, that would be pi halves minus negative pi halves, which is just going to be pi. All right, so the integral of 3 cosine x is a nice simple integral. Integral of cosine is just going to be sine. So we have 3 sine x, and we're going to be dividing it by our pi, again, because pi halves plus pi halves is going to be pi halves, or is going to be pi. And we're taking this from pi halves to negative pi halves. Okay, so let's take a look at this. So 3 sine x over pi, okay, is basically what we have here, this integral. Okay, I just wanted to take a look at it. Again, it's not whatever. So what we want to do here, this is actually our height here. So essentially, if we plug these in, we will get kind of our height that we want to look at, and then we're taking it and dividing it by the width of it. So I guess I should say it's the area divided by the width. That would be more descriptive, so it's actually the height that it's actually going to be describing. Okay, so if we plug in pi halves, quick refresher, unit circle, right? Pi halves is here, negative pi halves is here, sine is the height of our unit circle here. So sine of pi halves is going to be 1, so 3 over pi, minus sine of that's going to be negative 1, so that would be negative 3 over pi. And we get 3 plus 3 over pi, which will be 6 over pi. So okay, basically, we're creating a rectangle that is like this height here, okay? And it will have this width. So if you think about this, like x equals negative pi over 2, and x equals pi over 2. Basically, what we did was we created a rectangle of this size. So let's go ahead and plug this in over here. Well, paste it in here so that I can draw on it. But basically, what I'm saying is that we can find this area here. And if we find this area, it will be the same area as that shape. So let's try that out real fast, okay? So again, this is a width of pi and a height of this 6 over pi. So length times width is our area. So area is 6 over pi squared. Oh, I'm sorry. This is just a pi. Area is 6, okay? So that's our area of this rectangle. All right, so let's now take a look at this thing here, okay? Just that. So what's the area of this region here, just under the curve? Okay, well, again, this would be 3 sine x from pi halves to negative pi halves. Pi halves into sine is 1, so it's 3 minus negative 3, which is 6. So the area of our graph and the area of this rectangle we create based around the average height, okay, of this function will give us the same area. And so again, the reason why it does that is just because it is literally that's where it comes from. Like, that's how we find this average, is because we create some rectangle that will have the same area, and then you take the area and divide it by the width to get the length, and that length is the average height. So it follows that this would happen, but I just want to re-emphasize that fact, that we are finding this average function here. This f average is the average height of our function. Okay, and if we take the average height and multiply it by the width, we will get the area. Okay, so what value does that have? Well, let's talk about some uses for it. So first of all, the linear density of a rod, 8 meters long, is 12 over the square root of x plus 1 kilograms per meter, where x is measured in meters from one end of the rod. Find the average density of the rod. So if we want to find the average density of some object, if we can describe the linear density of it in some function, then we can find this average density. So all we're doing is we're going to take this thing, so we know it's 8 meters long. X is measured in meters from one end to the other, so at one end x is 0, the other end it's 8, so we're going to integrate from 0 to 8 on this rod, and we have the linear density here, 12 over the square root of x plus 1. And we're going to take it, and this would be the area of that region, but we want to find the average density of it, so that will just be the average of that function. So we're going to say b minus a, 8 minus 0. So we're just going to take this integral. Okay, so quick reminder, this is going to be 1 over 8 times the integral of 8 over 0, and this would be 12 times x plus 1 to the negative 1/2 dx. We should have that. We're integrating with respect to x. Okay, so what we're going to do here now is we could pull that 12 out if we want. We might as well, since there's already a constant out, but this is just a nice simple integral. We could do u sub if we need, but since this is linear and it's just a 1x, the derivative of 1x is just x, or excuse me, just 1. So no real need to use u sub if you don't need to. But if you need to, there's nothing to be ashamed of. You're welcome to use u sub. So we have 12 over 8 times the integral from 0 to 8 of this x plus 1 to the negative 1/2. Again, if you choose your u to be x plus 1, then your du is just dx. So that's why there's really no need to use u sub. But again, if it helps you, you're welcome to do that. So we raise this by 1. This would be x plus 1 to the 1/2. And we divide by this new power, 1/2, and then we would divide by whatever's being multiplied by x here, since it's a linear, but it's just 1, so we don't have to worry about it. We have 12 over 8 outside, and we're going to take this from 8 to 0. So let me clean this up a little bit, make it a little bit nicer. So first of all, 12 over 8 is going to be, they're both divisible by 2, so that's 6 over 4. They're both divisible by 4, actually, so that would be 3 over 2. Divided by 1/2 means times 2 over 1 times x plus 1 to the 1/2. And again, this is from 8 to 0. So we get 3 times x plus 1 to the 1/2 from 8 to 0. So 8 into here, 8 plus 1 is going to be 9. The square root of 9 is 3. 3 times 3 is 9. Minus 0 is 1. Square root of 1 is 1. Times 3 is 3. We got another 6, okay? So again, in this case, this 6 is our density, okay? That's the average density of this rod, and that would be in kilograms per meter here. So that's our average density of our rod. Okay, let's try another one. So in a certain city, the temperature in Fahrenheit, T hours after 9 a.m. was modeled by this function of T, the temperature at time T, is equal to 50 plus 14 times sine of pi times T over 12. Find the average temperature during the period from 9 a.m. to 9 p.m. So, first of all, this is T hours after 9, so at 9 a.m. time is 0. So our first time is 0, and our end time is 9 p.m., which would be 12 hours later. We're going to divide this then, divide it by 12 minus 0, and we're just going to integrate our temperature function here. So 50 plus 14 sine of pi t over 12. Okay, and we're going to do this with respect to t in this case, since t is our variable. All right, so this would be 1 over 12 times the integral from 0 to 12 of 50 plus 14 sine of pi t over 12. Now, in this case, because it's like, I don't know, it's still linear, but because it has some stuff here, you might feel like you need to call that a u sub, and that's totally fine. Again, nothing to be ashamed of as far as using u sub. You should use it when you need it. So if we call u pi t over 12, we'll see that basically our du is just going to be pi over 12. So essentially when we integrate it, we just have to leave it alone and then divide by kind of that inside here. And you'll see that in a sec because du is equal to pi over 12 dx. So we need a pi over 12, so that means we divide out a pi over 12, and that's where we get the division of pi over 12 later. So I guess we'll do that now. So dividing by pi over 12 is like saying times 12 over pi outside. So we can put in this like pi over 12 into this thing. We really only need it in, we can split this. Really, I can have the two integrals. I'm just kind of doing it all as one for the time being because it doesn't really matter. And since I have the constants outside of it, I don't feel like distributing them. So functionally, we're just putting in a pi over 12 into this so that we have, oh, not dx, a dt. So we have our dt here. So dt, pi over 12, that will become our du. And we're taking now the integral, the 12's cancel, and we get 1 over pi from 0 to 12 of 50 plus 14 sine of u, something like that we're integrating. So now, because we've changed this bounds of integration to u, this will be a 50u. So again, you could have split it and only done u sub for this one. It's all the same to me, so I'm just doing it here. Now, the other thing to note is that technically speaking, because we've changed our bounds of integration to u, we are no longer at 0 to 12. So I either change these bounds as we've done in the past, so I'm going to change these bounds of integration. Like in Calc 1, you may have done this, and we do it in Calc 2 depending on the situation, because we do a lot more integration, obviously, where basically our u is this t. So if we wanted to find these new bounds of integration from 0 to 12, we just plug in 0 for t. So 0 for t would be 0. So the new bounds of integration in terms of u would be from 0, and then 12, it would be to pi. And then we don't actually have to convert back from u's into t's at the end. So there's benefits to changing our bounds of integration when we do u sub. Sometimes I do it, sometimes I don't. It just kind of depends on the ease of it. If I don't do it, basically I stop writing the bounds of integration. So at this step and this step, I wouldn't write the bounds of integration so that I remember that I need to convert back into my other units before I use my bounds of integration. But since I already did this, we might as well stick with it. Again, where did we get this? Okay, plugging in 0 for t gives us a u boundary, and plugging in 12 and 12 cancel, leaving pi, okay, for our u boundaries. Okay, so it's this integral from 0 to 12, or 0 to pi, and I'm actually going to go ahead and do that integral. So this would be 50u plus the integral of this 14, we just leave alone as 14. Integral of sine is going to be negative cosine u, and we're taking this from pi to 0. Okay, so this would be 1 over pi times 50u minus 14 over pi cosine u. So I like to distribute that constant in when I'm doing this. Just makes my life easier, essentially makes it so I don't make as many mistakes. Okay, so if we plug in pi here, we have 50 times pi over pi, that's going to be 50. Minus cosine of pi, again, cosine is horizontal, pi is here, it's negative 1. Okay, so minus 14 over pi times negative 1 minus, okay, now 0. If we plug in 0 for u, here we get 0 minus cosine of 0 is right here. It's 1. So it's 14 over pi. Okay, so that means we have 50 plus this 14 over pi plus 14 over pi. So we end up with 50 plus 28 over pi degrees Fahrenheit, which that's not a very pretty thing. So let's go ahead and find what that approximately is and make sure that it's something that would make sense. So 28 over pi would be 58.9 degrees, give or take. So about 59 degrees, which would be a nice day for me. And it's a believable degree, at least. We're not somewhere like a million degrees or something like that. So it's always worth checking to make sure that at least the number is something that is believable. Okay. So, and if you think about this, we can plug in any time that we want. So if we do something like time is 0, right? When time is 0, we have sine of 0. Sine of 0 is 0 times 14. So apparently we started at 50 degrees, and it kind of fluctuated probably. So let's see what that function actually looks like. This 50 plus 14, since we have a sine function, sine of pi x over 12. All right, I need to zoom out a bit. Okay, yeah. So basically, and we're talking about this function from time is 0 to time is 12. So really it actually looks like this, where from 9 a.m. to 9 p.m. it went up, it then hit here and came back down. And so our value here, y equals 50, was it minus? Plus 28 over pi gives us this kind of average height. And that's believable as well on our function. And there's actually 2 times in the day where we hit it. And again, we expect to at least see once because of our mean value theorem for integrals. All right. So that is our average value of a function. Again, nothing too difficult. We're just taking area and dividing by its width, but it is a pretty interesting use for our integrals, and pretty simple thing too. So anyway, thanks for watching.